2024 class on cutting-edge web technologies. Today we are really honored and glad to have Matt from Meteor to come be the guest lecturer talking about Meteor. And Matt is one of the key creators of Meteor, and I'll let him do more introduction.
Thank you. Thanks, everyone. You may want to hold your applause until the end. You may not like it. My name is Matt. I'm not going to spend a whole lot of time boring you with my story. Let's just dive into it. So how many people know about Meteor? How many people have seen it? Cool. All right. So I don't know how much we're going to be able to talk about in 40 minutes. So what I wanted to try to do was give you a high-level overview from a computer science perspective of what we have tried to do here and why we've built it the way we have. Please interrupt with questions. I'm happy to take this off into the weeds whichever way you want to go. I have a few notes. If you go to cs294.meteor.com, it's just a gist, but you can follow along, maybe. We'll see if we stay on track. And just as an order of like some of the things I wanted to talk about. So Meteor is a platform for building applications in JavaScript. And maybe the first thing to talk about is what the hell is a platform? What's that different from a framework or a library or all these other things? And you're going to see a bunch of examples of this. But the interesting thing for me was I ripped the title of the class off of probably my favorite book when I was learning CS at MIT. Anybody know what the BSD Unix OS was? Probably invented upstairs or like around the corner. So this to me is one of the best examples of great system design that computer scientists have built. If you look inside Unix, and it's gotten a little more complicated, but you know the concepts of processes in a scheduler, the idea of a socket, the idea of mbuffs and system calls and traps and how a kernel works and the different parts relate, those things have allowed people to build an incredibly rich array of software on top of them because they were really well designed and thoughtful building blocks for a wide variety of apps. They respected the actual technology underneath them, like the hardware capabilities that we had back then. But they also abstracted you away from stuff you didn't want to deal with. Great success. So, there's a heritage there that I think we wanted to follow as closely as we could in writing modern web apps, where instead of trying to just think about a framework, which means like, I'm going to tell you where to put your files, and I'm going to give you some convenient functions so that you don't have to maybe pluralize a string or whatever it may be. We're going to think about this more from like a concept of building blocks. What are the right primitives for building a modern app? What do you need? What do you not need? And why has it gotten so hard using the technology that we've had around for a while? So enough yammering. We can talk about applications in history as having some different eras. So to set the stage, let me just draw some of that out. We can go back to the 70s. Can everybody read this? I'm not the best. I didn't go into writing. So in the 70s, we had what we could call the mainframe era. And I'm going to just draw a little diagram to represent what was going on back then. So in the mainframe era, we had a database. And the database was actually part of the application itself. So this was like, IBM 370s or something. And DB2 came as part of the actual computer back then. So you had some application that you wrote that ran on this giant computer in the data center. You had some kind of a network. And back then, this would be like 3270 or it would be VT100. And on the other end, we had a person using it. So this is time sharing. This is green screens, dumb terminals over here. The application would basically draw a whole screen. You'd look at it. You can still see this if you go to the airport, like the stuff the people are using to sell you a ticket is exactly this stuff. Something really interesting happens in the 80s, which is the PC era, or what some people would call client-server, right? And it's a very different picture. And in particular, what happened was we still have a database, which has now been broken out into a separate piece of software. So here's the rise of Oracle. There's a little bit of an app over here, but most of the application crawled down the network and lives over here on your PC. So the actual software you're running is next to the person using it instead of on the far end of the network connection. And the stuff on this network is totally different. So we don't send serial data with the screen. We actually send like ONCRPC, or Corba from Windows, Novell, all this kind of stuff. This may be way back in the past, but it's interesting to read about. It's data. So it's structured data instead of what we might call presentation screens that we put on the network in the 70s. All because Intel figured out how to make a cheap enough computer that everybody could have one on their desk. And all of a sudden we could write software that had windows. It was interactive, it had graphics, and all these other things that we couldn't do before. The 90s roll along, or 2000s, we get the web. What's different about the web? Well, it's actually this picture, right? I've got a database server in a data center. I've got a LAMP stack running on a computer in the data center. I've got a network protocol. This is HTTP over TCP. And I've got a user with a dumb terminal, except we called it a web browser, right? So this is presentation. And in particular, HTML is the language for the presentation, right? This is how we describe a screen. Same story as back here. I look at a screen, maybe I press a link, or I fill out a form and hit a button. The software draws me a new screen, sends it down the wire, and I look at a new screen. This is like yahoo.com back in 1999. So the whole premise of Meteor is based on the fact that we are now entering 2015, a new era, which I think it's fair to say is the mobile era. And guess what? History has a filthy way of repeating itself. We're back over here. I don't really know how to draw a phone, but I guess I don't really have keys anymore. But we have a person with a phone, right? Oh, we have a web browser, but now the web browser itself runs JavaScript, and it's basically a whole computer. You can do 3D graphics, sound, network connectivity, anything you want to do inside JavaScript from the browser. So it's a whole computer again that's on the client end. So it's really interesting, because if you dig into how people are building modern apps today, we're trying to use this stuff. We're trying to use HTTP, which is a request response protocol for moving documents across the network, to do something that actually looks a lot more like the 90s when we have data. We really want structured data, and we really want it flowing in both directions. And I'm going to dig into that in a little bit. So the reason writing software has gotten so hard is because we're using the wrong era's technology for the new kind of thing people are trying to build. And the way to think about Meteor is it's designed from scratch to be for this stuff. And again, you can jump in with questions anytime. Okay, so let's take a closer look at that picture for a second. What's actually going on is we've got some data in the cloud, and we've really got lots of people using it at the same time, which is the other big difference from the 90s. So we've got iOS people, we've got Android, we've got the people using it on the desktop. So we can call this HTML5 or JavaScript, right? And we really have millions of people, if I got that right. Yeah. So we're building a big distributed system. That's what modern software is. It's code that runs over here. It's code that runs over here, and here, and here. And there's data flowing back and forth all the time. Why is that? Well, a couple things about apps. First of all, they don't have any refresh button anymore. So, what's a good example of a modern application on the device? Uber might be a good choice. You don't have to hit refresh to see where all the cars are. You just see them moving around on the screen. So the whole experience is live updating, right, in a way that wasn't true before. So we need a way for all of these users to see information as it's happening, which is different from the web. Another example of this is collaboration. So if I think about Google Docs or a spreadsheet, or I think about a lot of the modern apps that we use on the device today, I see other people's changes as they happen. Even something like Twitter or Instagram, right? It doesn't have to be, high concept business software. We have this element of working together, of seeing each other's universes, which is again very different from what we had before. And of course, there's mobile, which means I've got software running on the client, and that software needs to be learning about new data. So we have a totally different problem than we had back in the web, which is we have to be able to push information in real time to each of these clients. And that's going to take us right into the architecture of Meteor. So what I want to do is draw it from the perspective of the data and the wire protocol, because I think that's a good way to think about how systems are built. So let me start by drawing you. We'll represent the network this way. So the server's over here, the client's over here. Okay, so 4 questions to think about. Question number 1 is, in a modern application like this, how does the data move between the different parts of the app? So we need to have a story that's akin to what we had with HTTP for web apps for how data is going to move back and forth. So that's the first thing I want to talk about. Then we're going to talk about, where does it come from? How does this data get onto the network in the first place? Where do we put it on the other side is the third question. And then how do we use it? So that's your map for where we'll go for 20 minutes or so. So let's talk about that network connection between the client and the server for a minute. In HTTP, how does HTTP work? It's a request response protocol, right? So there's really only one thing I can do in HTTP, which is the client can ask for something. That's a get or a post. And I get back, 200 OK and some data. That's the only thing you can really do. Pretty reasonable, since it was designed for getting documents, right? What better thing to do than ask for the document and get it back? There's no way to send data the other direction, right? I can't actually send information from the server to the client. There's some hacks we can use to fake it, but fundamentally it doesn't have anything like that. So we're going to replace that with a protocol called DDP, Distributed Data Protocol, which is going to run not over HTTP, but over a WebSocket. People know what WebSockets are? Do people really know what WebSockets are? People know what sockets are. So one of the original ideas from Unix is I can create a thing with 2 endpoints. If I put data into one end of it, it comes out on the other end in order and without changing any of the data. Pretty reasonable abstraction. So there's local unit sockets which stay on the same machine, and then there's the ones we're mostly familiar with, which are network sockets, so that I can have those 2 ends of the connection be on different machines. WebSockets are a steaming pile of crap that allow us to fake that from inside of a web browser. So a WebSocket is nothing more than your JavaScript code in a browser can now talk directly to an endpoint in the cloud, just like TCP. So reliable in-order packets go back and forth. But that's all they give you. It's very low level. It just says, like, if you put a byte in on one end, you'll get a byte out the other end. It's not framed. There's no discussion about the messaging that comes on top of that. So here's the thing. In the HTTP world, in the REST world, we have interoperability, right? I can write a REST client in any language I want, and I can talk to any REST API on the web, and it's very straightforward, right? I get to take advantage of all that common infrastructure. If there's a proxy server in the way, it doesn't matter to me, because I don't see that. But if we use WebSockets, I can't do that. So it's really weird when you think about it, but you can't connect Facebook's real-time API up to like Twitter's real-time API, because they don't agree on the language. They don't agree on the formatting or any of that stuff. So it's inevitable that there's going to be some kind of standard around how to do real-time data in an architecture like this. And so DDP is a very simple protocol that we use to do that. There's a link in the document that you can read about how the details of it work, but there's basically 2 halves to DDP. The first half is what we call a publication. Publication. So the idea of a publication is that in a live updating system, I don't just want one snapshot of data from the server. I want a continuous stream of information because it's changing. So the way we get that in DDP is the client asks or subscribes to a publication from the server. And what that means is the server starts sending documents and changes to documents. So you get added, change, and remove messages. And you just get a constant stream of them going into the client. So if, for example, I ask a Meteor server for the list of, there's a simple Meteor example called leaderboard, which shows a list of scientists and a score. So the client subscribes to the publication of that list. And that list is documents with a name and a score for each item in the database. And as the scores change, or as people add new names, those are messages that go down the DDP connection to the client. And you can actually, there's a command line tool that lets you inspect that, and you can play with it. So this is sort of like a GET in REST, except live updating. So it's a subscription. The other half of this is, how does the client ask the server to do something? Well, that's really easy because we can look at what client-server architectures did in the 90s, and the answer is an RPC. So a remote procedure call, what we call a method. And a method is just basically a function call over the network, right? So the method might be add to score, take some arguments, and then the server replies with the result. Very simple. So DDP, that's all you need to know. It's JSON data. There's publications and subscriptions. There's RPCs. And then there's just a little bit to tidy the two up together. And there's one trick we play that I'll get into later to do something called latency compensation. Make sense? So in Meteor, you can rely on the fact that there's a standard protocol and start to add other parts to the system. So for example, there are DDP clients for iOS or for Android. So you could actually have a Meteor server over here written in JavaScript, but you could have a native iOS app if you wanted. And the other end of the wire doesn't have to know how the far end is written. You just have to agree on this basic interchange of messages. OK, so just a footnote. EJSON. So as an example of the kind of detail work we have to do when we think about this kind of stuff, how many people know JSON? So how do you represent a date in JSON? What's the string? It's a mess, right? So JSON is a way of serializing JavaScript into strings so that we can send it over the network. But the problem is it doesn't have all the stuff you want as a developer. So EJSON is an extension of that where we agree on how we're going to serialize dates, and we agree on how we're going to serialize other types. And so you can read about some of the details of that at the link. OK. So question number 2. So that was, maybe I'll just write them up here. One is, how does the data move? Question 2, where does it come from? Well, where should it come from? Any ideas? Where does data live in most apps? Where in the server? The storage tier. Yes, a database, sure. I like that, though. That's good. So there's this basic problem in almost any modern live updating app, right? Which is, I have some data in a database, and I want to push updates, right? So as it changes, I want to see those changes, and I want to send them down to clients. So we know how we're going to send them. We're going to put them into DDP subscriptions, right, and push them across the network. That's great. So now the next question is, how do we watch a database for changes and then put them onto the wire? So Meteor, so in most apps, the way this is done is people write a bunch of special purpose code on the server to keep track of every incoming change, figure out who's allowed to see it, and then basically orchestrate which connected clients are going to get to see that stuff. So you end up writing a lot of messy code, security code, right, that has to run whenever someone does an update. There's a couple problems with that. One of them is it's a lot of code. The other one is if someone makes a change to the database directly, you don't know about it, right? It didn't come through your code path in the app. So Meteor does something more general purpose, which is to observe a query. So observable queries. So how's that work? Well, the idea is pretty simple. If I do a query, so we'll use Mongo syntax for this because that's what we generally use at Meteor. So let's say I have, name Joe, score 10. So that's one document in my database. And then I have name John, score 20. So I can do a database query. I can ask Mongo, give me all the players with score 10 or above, and I would get back 2 documents, right? What I actually want to do is I want to watch for that. And I want to, anytime that query result changes, I want to be notified with a callback that there's either a new document in the result set or that one of the documents has changed. So let's say someone changed Joe's name to Joseph. I want to get a message that says, any client that thought the name was Joe, we need to tell them, right? So we're going to have to send an update from the query. Or if a player's score is set to 0, I have to remove one of the rows from the result set. So there's add, change, and remove that come out of the query. But Mongo doesn't do that. Mongo's like a normal database, just like SQL, where I ask it a query and I get back an answer, and that's it. So any ideas for how I can turn a traditional database into a real-time database? Any strategy I might use to see those changes? Any idea? What would you do if you were faced with that problem? It's a reasonable design question, right? Yeah?
I mean, you could wrap the database with some wrapper, and then you could set flags for different fields that change, different fields that are observed, and know which clients to update, certain fields that change.
That's right. So one strategy is watch every incoming update to the database and know, based on that, what to do. So I like that. The problem is it's fragile because you now have to watch every database update. So this gets much harder unless I really wrap the whole database. Now I'm building a whole database at the same time, but it's reasonable. Yeah.
Rerun the queries and then check the output.
Sure. Rerun the query and compare to the last time. And that's, in fact, the first thing we shipped with. Something called poll and diff is what we call it. So here's my data set. Let's just say I ask for all players, just to keep it really simple. So I get back this result. Then let's say I set score to 10, or I guess I already have a 10. Set score to 30. I rerun the query and I get back Joe 10 and John 30. And now I have what turns out to be a pretty gnarly CS algorithms problem, which is compute the minimum set of add, change, or remove events that transform an old query result into a new query result. It's not totally obvious how to do this. I mean, in a simple example it is, right? But there's a really elegant piece of code in Meteor that does that. It's like least change. I forget what we called it, but because you can imagine. Oh, and the other thing is there's ordering to these queries. So there's also a moved event that can happen. So you can actually represent moved as insert and delete, or just a move. And so there's some tricky problems there. What's the downside of poll and diff? There's 2 big ones, I would say.
Super expensive.
Super expensive. Yeah. In particular, why is it expensive?
You're hitting the database all the time for the data to change.
Yeah. So we're hammering the database with queries. This doesn't look so bad, but what if the result set had 10,000 rows? And what if in practice they don't change very often? So all the time I'm paying all that I/O cost across the wire, and then I'm paying all that computation cost. It turns out the diff is expensive just to find, it's all the same. What's the other problem with polling? Besides being expensive, just architecturally, what's the downside of a polling strategy?
You only get updates at regular intervals.
Latency, yeah. So there's a trade-off of how often do I ask, anything changed? Anything changed? So I can up that frequency if I want, which compounds the cost problem, or I can drop the frequency if I want, which means it's going to be a while before I notice that something happened in the database. That's a bummer. But there's a big advantage to poll and diff, which is it works. And I don't mean that lightly. The point is the database is the source of truth. And if I ask the query a second time, I'm going to get the current values. And so I know that my data is correct. And it's a very simple algorithm. And there's a lot to be said for simple stuff that you know is correct. We can move on to other parts of the stack and not worry about this. But for most production apps, this isn't going to work. So what we do instead, in most cases in Meteor, is what we call oplog tailing. So how does oplog tailing work? Well, it turns out MongoDB emits a log of every update that's made to the database. The reason it does this is because this is how it implements failover. So normally when you run Mongo in production, you actually do something that looks more like this. This is called the master. And these are secondaries. All the writes go into the master. Any change in the master is then sent through the log to every other secondary. It's actually a pretty elegant way to do this. If the master dies, then there's an election that's held. One of these decides it's going to be master, which is another interesting CS problem, right? Prove that you can always pick one winner, and the oplog starts flowing from here. So it turns out we can tap into that log, and we can watch inside Meteor all of the changes coming from the database. So this is an interesting problem because the oplog doesn't have all the information we need. And I think in the interest of time, I'm not going to go through all the examples of how this works. But to give you a taste of this, let's say I have that same data set. So I've got Joe has a score of 10, and I'm really abusing Jason now, but you get the idea. And Jason, God, that was terrible, has a score of 20. And let's say I'm running a query, find score equal to 10. Does that make sense? So I want to know everybody who has a score of exactly 10. So in poll and diff, we know what we would do. We would run the query, give me all the people with a score of 10, and see if the results change. With oplog tailing, every write that happens in the database turns into a message that we can look at to see if our results may have changed. So let's say someone inserts a record, Matt 12. And that's what's on the oplog. It's add new record with Matt 12. So do my result sets change? No. No more work to do. I can quickly look at that row and realize it's not in play. Let's say, and actually oplog operations are always what we call idempotent, right? So they're actually going to be a bunch of sets, and there's a reason for that. It has to do with guaranteeing that we're consistent across the databases. So let's say we get an operation on the oplog that says set Jason's name to, I don't know, Jack. So do my result sets change? How do you know? I mean, Jason didn't have a score of 10, right? So he's not part of the result set. So when I get this operation, what I can do is I have a state in here of what the current answer of the query is. And I can just look at the fact that, well, I don't have Jason's document. That's not part of the answer. So the fact that he changed his name can't possibly affect the score being 10 or not. It obviously wasn't 10 before, so it doesn't matter. So I can look at this and know I don't have to do anything. On the other hand, if we get a message that says set, Joe's name to Joseph, does that affect the query? Yeah. And so there's a bunch of cases here that you can case out. There's a link in here to a talk that goes into a lot of detail. That talk alone takes an hour, so we're obviously not going to get through it. But you can, based on the set of operations coming over the oplog, in many cases avoid ever talking to the database to keep your real-time query result up to date. And in other cases, you have to go back to the database for more information, but you're not pull and diffing. You're just grabbing one whole document that gives you the rest of the information you need to know. Yeah.
So so assuming you can tap in and just get all the operations.
Yep.
Doesn't the time of checking whether this new operation affects our current data set or not just grow linearly with just the size of our data that we're keeping track of? So it could grow really slow as there's a lot of things that keeping track of.
It grows linearly in the number of updates. Yeah. So that's right. The point is, as the write workload on the database increases, the server has to do more and more work, much of which be totally unrelated to the queries we're watching. That's exactly right. That is, in fact, the current scaling, the current thing you typically run into first in a high workload environment with this strategy. There's some pretty straightforward optimizations. So we could write a little oplog proxy that knows how to decimate the oplog for only the collections we're watching or for only the queries we're watching. The other recognition is we can do this as much as we want. And so this is horizontally scalable, right? Yeah, we have to pay for the CPU, but CPUs are pretty cheap now. What you really want to avoid is a situation where there's only one worker that can do the thing. And this actually doesn't have that problem. Turns out when you do this, the bottleneck is I/O bandwidth outside of the master. Because you can't register 1,000 oplogs on a database. The database will spend all its time sending that information out. And so there you probably do have to build a proxy so that it can fan out. Questions about oplog? Yeah?
What do you do if your Meteor server crashes? And you have some internal state about what you're watching?
Great question. So what do we do if we crash and we have this state and we don't know where it is? There's actually lots of situations like that. Another example is what if this thing just falls behind? In other words, what if that pace of updates is so fast that the server just can't, there's a queue and the queue keeps filling up? So our answer is we give up and we go back to pull and diff. That's what I was getting at before. The nice thing about pull and diff is it's correct, right? So it's good system design. Even though we know there's some downsides to this, we always have a fallback that is going to give us the right data. So if the server crashes or if we can't keep up with the incoming data into the cache, we can just reset to the current value of the database. The other trick for if you're playing at home, it's very hard to correlate the oplog to the actual state of the database. So you can't, if you start watching the oplog, you start getting a stream of messages about what updated. How do you know when you do a read in the database where in the oplog sequence that read happened? It's not obvious at all. So you end up needing strategies for putting a marker in the oplog or for proving that you have the right spot in there. It's probably a whole master's thesis wrapped up in there somewhere. Okay. Well, obviously we're not going to get through the whole thing. So let me talk about what do we do with it. And this will give you a really nice sense of like the overall architecture. And then I think we'll do questions and I can get into whatever people want. So what do we do with it? What do we do with it? So here's an interesting thing. Let's go back to that architectural diagram. I've got the database in the cloud. I've got a network connection. And then over here, I've got my app running on a phone with the user. This is a high latency network, right? This could be a mobile network. This could be, I don't know, 100 milliseconds. It's not reliable. I might drive through a tunnel. I don't actually have service down here. Turns out it's a non-starter for the application logic to go ask questions about this database, right? It's not going to work. So part of the reason for this whole pub-sub architecture is that there's data that's changing, so we have to have a way to inform the client. But there's another reason, which is we have to cache the data on the client for this to work at all. Because if my code over here has to pay this cost for every query, the application is going to be really slow. So you'll find a cache inside any modern app that's running in this style, not just Meteor. But what we've done with Meteor is we've done it in a general purpose way that you can take advantage of. So this is the actual architecture in Meteor. So Pete Hunt was here last week, told you about React, and I think probably told you how it compares to some of the other view layers. So this is the view layer of my app. And the observation is, if we know the data has changed, we can redraw the screen. That's great. So I'm not going to tell you any more about that. Everything Pete says is right. Except if he gave you some crap about observable key values, we can talk about it later. But they make good stuff. So the cool thing about an architecture like this is if I have application code and I want to do a database read, and all I have to read from is my local cache, it's fast. So that means I don't have to be really careful about how I write my application code. I can just write the obvious stuff, kind of like how you do in a Rails app. It's no big deal, because it's not like your queries are super performance sensitive. So this is the Meteor architecture, is I have observable queries, so I can efficiently know about changes to the database. Those queries get essentially sent as subscriptions over DDP, over a WebSocket, and that data is stored in a cache. And the neat trick is, what's the query language for the cache? It's the same API as the query language on the server. So I don't have to learn separate APIs. And in fact, in some cases, I can even share code. So most people don't actually do this, but like there is a case where simple things like validation logic or other things where I'm doing just simple queries about what's in my database, literally the same module, I can write a single file and use it both in the client where it's talking to the cache and the server where it's talking to the database. So the life cycle of data in Meteor is if I do a query, let's say back high score list, I run the observe on the server pushes it to the client, stores in the cache, and then I've got a template, my view layer, which is running a query. It's basically saying, make a div for each, name in the database and put it on the screen. And as the data changes, as I get, a new score that's set to 30, that changes the score over in the cache to 30. That triggers an invalidation, which runs the template, which puts it back on the screen, and now I have this live updating app experience. Yeah?
Could there be conflicts between the cache and the database if someone else changes the database?
Conflicts between the cache and the database if somebody else changes the database. You're the winner. You get the last 5 minutes. Okay. So who's changing the data? Who are you worried about?
I don't know, some other user maybe if they're putting in something under the reading.
Yeah.
Maybe even someone who can access the database.
Great question. Okay, so let's talk about the data architecture here and conflicts on writes. So this is a great question. I love it because this will show you our philosophy about how to design systems, which is to keep it simple and don't get yourself passed into a corner where you can't reason about these things in a good way. Okay, so point number one. The only writes into the cache are coming from DDP, which is coming from the server. So that's nice. It tells us that the cache may fall behind. I'm not guaranteeing how fast those updates are coming. Maybe the network gets lost for a while. But over time, eventually, the cache will reflect exactly the live query that I asked for from the server. That's good to know. That means I don't have to worry about patching it up later. Point number two is those changes are being driven by a database query. So part of the answer to your question is, how do we handle conflicts when two people change the database? Our answer is, it's up to the database. So in Meteor, with Mongo, the answer is last writer wins. In other words, in Mongo, if you do a write, and you're the last one to change that document, congratulations, you changed the document. In a SQL database, it's much more complex, because in SQL I can have a transaction, so now I have isolation between transactions. That means if I do a write, I may think I've done the write, but in fact, another person can come along later and have their transaction invalidated because I changed the data out from underneath them. I don't know if you guys have looked at how databases work, but there's some real sophistication in there about it. But the point is, we're not going to make some shit up The rules are the rules in the database. That's good because people spent a long time figuring this stuff out. What I'm not going to give you is some bizarre answer involving like multi-master, like OT, maybe we'll merge some data according to some rules that mostly work. Like, no. That's a good way to write bad software. There's one other trick, though, which is, let's say I'm the user over here, and I make the update. Let's say I change the guy's score. So there's one huge problem with this picture, and that is, how would I normally do that in Meteor? I'd call a method to change the score. Message comes over here. Presumably that writes to the database. The oplog tailor sees that, sends back an update message, updates my cache, which redraws my screen. You can't do that. Because the round trip to the server is too slow. You can't lag your own interface by that amount. It's just a really janky experience. And you'll actually see badly written apps that do that. Like you type in a chat message, but then like the screen freezes for half a second before everything updates. It's like, yeah. So any reasonable app is going to have some fast path where a user's writes are immediately visible on their own screen while all this is happening. How do we do that in a reasonable way? Well, here's the answer. This is something called latency compensation. And it works like this. When I do a write, I do an RPC, so update score. I am also allowed to write to the cache, but in a very peculiar way, which is I fork it. So the cache in Meteor, and this is actually done on a document level, but we'll draw it as the whole database just for our purposes. There's actually 2 copies of the cache in the client. One of them is the cache that we've been talking about up to this point. So what the server believes needs to be in there, the only person that writes to this is the server. So we'll call this truth. The other one we'll call speculation. Because what the client's going to do is it's going to speculate what the server is going to put into the cache and just do it right away. And in the case of updating the score, I'm pretty sure I know what's going to happen, right? So I'm going to immediately update the score in the cache. Reads do not actually come out of here. Reads come out of the speculative cache in Meteor. So now we've got the true values, we've got a speculative value, and any writes I do are immediately showing up on the screen. So there's one last question, which is, how do I resolve a conflict? What if my speculation was wrong? The answer is, we throw it away. So we only have this fork so long as there's an outstanding method on the wire whose results we have not yet gotten back. And I told you back when we were talking about DDP that there's a special hook in DDP to make this work. It turns out the hook is this. When I do a method call, DDP will tell me not only when the method returns, because there's a value, right? It's like calling a function, so I get a value back. But DDP also tells me when any observable query affected by that method has all of its added, change, remove messages queued up on the wire. In other words, the client knows when it has now seen all of the data changes that were a result of a method. And it turns out, and I think given the time, I will leave this as a puzzle for you to think through. It turns out, once you've seen all those updates, it is safe to throw away your speculation and just drop the actual true value of the cache into there. And then the screen updates to what the server actually decided. The nice thing about this is, I know that any speculation I do on the client is only in the client, and I know that eventually it will simply go away. I'm not trying to resolve it with something else, I'm just throwing it away. So it's nice and clean and simple, and it's provable that in the long run, eventually, each client sees exactly what the server's been publishing. Yeah?
Does that mean you might occasionally have a situation where the UI updates and then deletes what it did and says, please disregard that, you didn't see that?
Yep. And
disregard that.
I think we're out of time, so I'll just say, yeah, that's possible. It's up to the programmer. So what I've described is a good system for reasoning about this stuff. you don't have to write a speculative update if you don't want to. So if you were building Amazon, you probably wouldn't speculate that the purchase succeeded. You actually do want to wait for the server to tell you.
They speculate on the server side.
Well, that's up to them, right? But the point is, like, it's a program-level decision, an application-level decision, when you want to anticipate the write and when you want to actually wait for the server. And that's not something your platform is ever going to figure out for you. That's something that actually does depend on what you're trying to do. So Meteor makes it very easy for you to do that when you want, but not to have to always have some sort of conflict being resolved if you don't.